Great. Good morning, everybody. Welcome back to Abstract Algebra. Plan for today is we're going to continue our discussion of permutation groups and get into a special type of permutation group today called the Symmetric Group. I've got my usual office hours this afternoon from 2 to 3, and tomorrow morning from 10 to 11, and tomorrow afternoon from 1:30 to 2:30. And as far as homework goes, don't forget, homework 4 is out and will be due on Friday. How could you forget, indeed, I know. Okay, good. There we go. Yes?
Do you have another packet? I'm assuming it was good on Monday.
Oh, permutation packet? I did not bring any to class, but they are posted on Blackboard. You can go and download a copy of it.
Thank you.
Are there questions or comments? Why did the young Angle have such a hard time getting a loan? He had such a hard time getting a loan because his parents refused to co-sign. Quite. Up there, his parents, not that loud. Okay, so you may remember, yesterday we began talking about what it means for a function to be a permutation. We said that f from a set A to the same set A is a permutation. You have to include the actual relevant one. If it's one-to-one and onto, where f is one-to-one, if whenever we take two elements in the domain, if we have two elements in the set A, such that f of A equals f of B, it has to be the case that A equals B. In other words, our function is going to be one-to-one if no two elements map to the same thing. And our function is onto if given every element in A, if given any element in A, we can find something that maps to it. So given any element A in A, there exists some element B in the same set such that A is equal to f of B. We can always find something that maps to everything in our set, then it is onto. And if our function is both one-to-one and onto, then we call it a permutation. So I wanted to start out by kind of going through these three examples that we looked at towards the end of last class. Kind of gave you all a chance to look at these, but we never talked about them. And I wanted to determine for each of these if they form a permutation. So let's start off with the function f going from the reals to the reals. F of x equals x cubed plus 1. And my question is, first of all, is this function going to be one-to-one? Or is it possible, or is it not one-to-one and you can find two elements that map to the same thing? What are y'all's thoughts on this one? Yeah, Peter?
I believe it is one-to-one.
You believe it's one-to-one, that no two elements can map to the same thing?
Yeah, because even if you take a negative, you're going to be we're taking it to the third power, which means you're going to head with a negative element rather than a positive element, like if you had x squared. Sorry, there was a hitch in my thought for a second. I fixed this.
No problem. You got it. Yeah, we don't have the same problem that we do with x squared, where you can't take like 2 and negative 2 squared come out to the same thing. If we want to prove that this function is one-to-one, we can just take two arbitrary elements, I'll call them x1 and x2, and we can say if f of x1 is equal to f of x2, then that, by definition, that's going to mean x1 cubed plus 1 is equal to x2 cubed plus 1. We can do the old swoosh swoosh, and that'll tell us that x1 cubed has to be equal to x2 cubed. Subtract 1 from both sides. And if x1 cubed is equal to x2 cubed, does that mean x1 has to equal x2? Indeed. Yes, I agree with Peter. I do believe this function is one-to-one. How about onto? Given any real number x, can we find something else in the real numbers that when we cube that something else and add 1 to it, that'll give us our x? Right?
Oh, yes.
You claim the answer is yes?
I forgot what you said.
Basically, I'm just asking if is this function onto, meaning
Yes,
given any.
onto.
Right, let's see. So, given any real number x, what can we say x has to be? We have to find something that's going to map to x if we want to prove that this is onto. By taking an arbitrary x in the reals and showing that it has to be equal to f of something. What would be a real number that if we cubed it and added 1 to it, we would get back our original x? Alright?
Like if you rearrange it or something like that, so then it's a minus 1 quantity to the 1/3.
Like that?
Yeah, or x minus 1. Sorry, that's 8 and 9.
It doesn't matter what we call it as long as you're consistent. Yes, absolutely. Since if you were to take cube root of the quantity x minus 1 and cube that and add 1 to it, you'll get back our arbitrary x. This is indeed an onto function. Because given any x that you start with, you can always find something that will map to it, and the thing that will map to it is just going to be cube root of the quantity x minus 1. This one's 1-to-1. This one is onto. It is indeed the permutation of the real numbers. Neato burrito. Any questions about this one? How about the function g going from the integers to the integers? G of x is equal to 1 minus x squared. Is that one going to be a 1-to-1 function? Here.
No, because we just do like -3 and 3.
So let's see, if we were to take g of -3, we would get 1 minus 9 is -8. And that is equal to g of 3, but 3 is not equal to -3. So this function is not 1-to-1 because we can find two elements that map to the same thing, 3 and -3. In truth, we can find infinitely many pairs of elements that will map to the same thing, just any integer and the negative of that integer. But a single counter example like 3 and -3 is all it takes to break our function being 1-to-1. Is g of x a permutation? Okay.
No, because it's not 1-to-1.
It's not 1-to-1. Automatically breaks it being a permutation. I'm going to check onto anyways, even though we don't need to for the purposes of determining if it's a permutation. Just because, good practice. All right. Given any integer, can we always find some other integer such that 1 minus the second integer squared will give you the original one? Okay.
27.
27! What a great choice. Yes, 27, what a great choice. So 27 is certainly an integer, but no element in the integers, or let's say no x in the integers, satisfies g of x equals 27. That's enough for our function to not be onto, because nothing will map to 27. And in truth, there's a lot of integers that won't get mapped to. In particular, any integer greater than 1 will not get mapped to here, but all it takes is a single counterexample, such as 27, in order to break the function being onto. So this function's worthless. It's not 1-to-1, it's not onto. You can't do anything fun with it. Doesn't make a nice problem. How about this third one? So this is our example where our function took all of you out of your seats and put everybody back down in alphabetical order. So here, our set that we're doing, A, is actually going to just be the set of all occupied seats in the classroom. And our function basically takes in, takes in a person's old seat, and it's going to spit back the same where that person ended up sitting after being rearranged in alphabetical order. So here's my question. Is this function one-to-one? I'm picking all of you up and putting you right back and putting you back down in the same set of seats, but in a different order, in alphabetical order.
Yes, if each input of the old seat is going to match a different new seat, different things of like different what everybody else's output.
It's a unique output, yeah. No two people, if I tell you rearrange yourselves in alphabetical order, I really hope none of you try and sit in the same seat. Got to do social distancing, right? So this one is going to be one-to-one. It's one-to-one since no two people end up in the same seat. Is this function onto? Where set A is the set of all currently occupied seats in the room. Is every seat going to get mapped to by some old seat?
Not going to lose any people. We're not going to gain any seats.
Not going to lose any people. We're not going to gain any seats unless Dr. Versal decides to be a troll and sit down halfway through doing the function. The set of full seats at the end is going to be the exact same set as the set of full seats at the beginning of the process. So I would say this is onto. Any seat occupied at the end of the process must have been occupied at the beginning as well. So, is this alphabetical orderizing function going to be a permutation? Indeed.
So if we're dealing with a finite set and our function is onto, does that mean that it's also one-to-one?
Good observation. Yes. If our set is finite, then it will be then any function from a finite set to itself will be onto if and only if it's one-to-one. However, that does not hold true for infinite sets, like we saw yesterday with, for instance, a to the x equals e to the x as a function from the reals to the reals. That was an example of a function that is one-to-one, but not onto. However, it does turn out to be the case, and I don't really want to get too deeply into why quite yet, because we're sort of actually going to see that later in the semester in a different context. It will turn out that if you're looking at a finite set, A, then a function from A to A is one-to-one if and only if it's onto. Yes? Any other questions or comments before we start talking about our group structure? Okay, so now we know what permutations are. We can actually talk about what is a permutation group. And in general, the group elements are just going to be these individual permutations for a fixed set A. So in general, you could say that the permutation group on the set A is given by the set typically referred to as S sub A, which is, as a set, it's just going to be the set of all permutations from A to A. So the set of all functions from A to A, such that f is 1 to 1 and onto. And so our permutation group the set is going to be the set of all permutations of the same set A. And the group operation is just going to be f star g is just going to be defined to be it'll flog the composition of functions f and g. So if you had some element in the set A and you wanted to do x star g defined as how it acts on A, that's just going to be, or x, whatever I'm calling it, that's just going to be take g of x and then take f of that. And that's our group. Our group is just the set of all permutations on a fixed set A. And the operation is just function composition. Where have we seen an example of this type of group before, where our group elements were functions that were permutations on some set of objects, and the way our group operation worked was you just compose two of these functions together. Yeah, the dihedral groups. Dihedral groups are all going to be examples of these permutation groups. Where the set that their permutation groups on is just going to be the set of configurations of regular n-gons. Configurations of. So here, our set A, if we're looking at the dihedral group, our set A is just going to be the set of all the ways you could take like a triangle or a square or whatever and just configure it, whether it's 1, 2, 3 or 1, 3, 1, 3, 2, the configuration of all the different kind of corners. So that's a group that we've seen several times and kind of done a bunch of examples with throughout the first few weeks. Let's take a look at another one. Let's look at the permutation group on the set of all real numbers, S of R. And so here, I'm going to take two elements in this permutation group. I'm going to take f of x is equal to 3x cubed plus 1, and g of x is equal to 2 minus 5x. What would we get if we were to take f star g? If we were to take these two functions, f of x and g of x, both of these are going to be elements of the permutation group, because both of those are going to be one-to-one onto functions from the reals to the reals. What would we get if we took f star g here? We would get another function from the reals to the reals. And what would that do to a value x? You do not need to simplify your answer. Yes, Lynn?
It would be 3 and then parentheses 2 minus 5x and then that cubed plus 1.
Bingo. Yeah, we would just get f of g of x, which is f of the expression 2 minus 5x. And if we're taking f of 2 minus 5x, then anywhere we see an x in the formula for f of x, we're just going to replace that x with a 2 minus 5x. So we end up getting 3 times 2 minus 5x cubed plus 1. Indeed. which, if you're curious, comes out to negative 375x cubed plus 450x squared minus 180x plus 25. Elaine, you weren't curious?
No.
I wasn't really either. How about a G star F? That's going to be G of 3x cubed plus 1. What's that going to come out to? Here?
It'll just be 2 minus 5 times 3x cubed plus 1.
Yeah, so it's going to be this expression, which is the same as negative 15x cubed minus 5 plus 2 is minus 3. What did we just prove about this group? Or, dare I say, which property did we just show this group does not have?
It doesn't have
It's not. It doesn't have commutativity. It's not an abelian group. So in general, f star g is not going to give you back the same function as g star f. So s of a is not abelian. And I can already hear Nick trying to come up with a counterexample for that. Yes, Nick, if your set only has like one element in it, and so the permutation group only has a single function in it, then yes, that would be an abelian group. But for most permutation groups, they are not going to be abelian because f composed of g in general is not going to give you the same thing as g composed of f. Which is something we saw when we looked at the dihedral groups. Those were kind of our second example of non-abelian groups, first being matrix groups. What's the identity element of this group? It's going to need to be a function that takes in it's going to need to be a function, meaning it's something that has to take in elements from the set A and spit back out elements of A. But under this group operation, what do you think the identity element would be?
X.
E of x is x?
Yeah.
Let's see. If we were to take some function f star e of a value x, that would be like taking f of e of x, which is just f of x. So f star e is just going to give us f. And e star f is going to be e of f of x. Well, if our function e just takes in something and spits back out the exact same thing, e of f of x should also be equal to f of x. I like it. Yeah. So it turns out that just like how in the dihedral group, our identity element was the permutation that picked up like a triangle or square and put it right back down in the same configuration. In general, the identity element of a permutation group is just going to be the function that takes in some x from your set A and spits back out the exact same x. As observation. Finally, how do we find inverses? Here, this is good. I like how everything sort of ties together from math. Looking at this,
Even be the inverse function of what your eventual function is.
it is indeed the inverse of an element in a permutation group is just going to be the functional inverse, which you may have seen from pick your favorite calc class, calc 1, calc 2. We talked about inverse functions. Those inverse functions happen to be the inverse elements of that function in the permutation group. Just like how when we were looking at our matrix groups, our inverses were just take the inverse of your matrix. or an inverse in both contexts refers to the fact that that is how you take an inverse of an element in some group structure. Take the function inverse. I.e., if you have some function f of x that's a permutation on A, f inverse of x is defined to be the function such that f composed with f inverse of x is going to be equal to f inverse composed with f of x, which we just want to give us back e of x, which is x. It's the function that you need to compose. The inverse of f of x is going to be the function that you can compose with f of x and get this identity function that does nothing to x. So if this formula looks familiar, that's just our formula for how inverses need to be defined in a general group. Except this time it's being applied to looking at functions specifically. If we do a quick example, let's take f of x is equal to 27x minus pi. And this will be a permutation on the set of all real numbers. Does anyone remember the trick for how, given a formula for f of x, you can find a formula for f inverse of x? Becca, any questions?
Alright, was getting clarification what I thought.
Mosquito. What's our procedure for, anybody remember the procedure from the previous math class for finding an inverse?
You said you can just do, well, I don't know if this is the prior procedure, but you can do y is equal to 27, x minus pi, and then you solve for x rather than solving for y, and then you can just switch those around. So the inverse will give you y is equal, or f of x is equal to, or f of x inverse is equal to whatever
Yeah.
you solve for.
Yeah, that's right. You set y equal to 27x minus pi, and then you do a switcheroo with your x and your y. And you can either solve for x first and then do the switcheroo, like I think what you said, Peter. My preference is do the switcheroo and then just solve for the new y. But either way, it comes out to the same thing. So in this case, when we do our switcheroo, we're going to get x is equal to 27y minus pi. What do we want to do with this if we want to solve this for y? You're on a roll. Who else can help me solve this for y? Becca?
Add pi to the other side.
Add pi to both sides.
Divide by 27.
Divide by 27. And this is going to be the formula for our inverse function. It's going to be 1/27x plus pi over 27. Any questions or comments? I've got a question for you. Lauren, you already think the answer to my question is, you're going to answer no to my question. My question is not a yes or no question, so you're already wrong. So here's my question. Why did we restrict ourselves to only looking at functions that are one-to-one and onto? Why couldn't we have just looked at the set of all functions from A to A and tried to make a group structure out of it?
Well, for one, if it's not one-to-one, then we'll have a problem finding inverses because we'll be able to solve for y. That would be anything.
Yeah. Basically, the reason why we need only one-to-one and onto functions is if your function is not one-to-one and onto, it's not going to have an inverse. And so, let me write that down. We need only one-to-one and onto functions, since these are going to be the only functions that turn out to have these inverses. And only permutations Because, for instance, if we tried to do g of x is equal to x squared, this is something that's very, as a function from the reals to the reals. We talked last time about how this is very much not a one-to-one and not an onto function. We tried to do the old switcheroo method on it and say, let's swap our x and y and get x is equal to y squared. What would we get if we tried to solve that for y? If y squared is equal to x. Here?
Plus or minus x.
Plus or minus x? I think it's plus or minus x per se. I think we need a square root in there.
Yeah.
And what's the problem of saying f? And what's the problem of trying to find an inverse function in this way? Saying f inverse of x equals plus or minus square root of x.
Inverses have to be unique.
Well, we would have to have a unique inverse, yeah. And the problem with this thing, is it ain't a function. It's something that takes in a single input x and spits out two outputs, or no outputs, if x is negative. This turns out is not a function, since if x is negative, this is undefined. This, let's just say, does not exist. If x is positive, this gives two outputs. And if x is 0, then it actually works. It only gives a single output. Done. So basically, you're always going to run into this sort of problem where if your function is not one-to-one and onto, you're not going to get a well-defined inverse function that goes from the same set to the same set. Questions or comments? Okay, talk break. Okay, talk break over. So that's the general structure of a permutation group. What I want to do now is I want to talk, as the rest of this packet, we're going to be focusing on looking at a specific type of permutation group. And this one is not going to be the dihedral group, but it's going to be a group called the symmetric group. So the symmetric group is basically just going to be, it's just basically going to be like a permutation group on a finite set. At least the ones we're going to be focusing on. So the symmetric group of order n is the permutation group of the set A, not of order n, because the order is not going to be n. It says symmetric group of order n in your packet. That's a lie. Erase that. Symmetric group on n elements, let's say, is going to be the permutation group on the set of all positive integers from 1 up to n. So S3 is going to be set of permutations on the set 1, 2, 3. We can do the permutation group on the set of all integers from 1 up to 27. And in general, we're just going to be looking at, with these symmetric groups, permutations on these sets of positive integers. So let's look at S3, which is going to be permutation group on the set of integers from 1 to 3. let's say we wanted to, I want to make a list of what do all of the elements of this symmetric group S3 look like. And so, since our function is defined, any of these functions is going to be defined by where it maps the three individual elements. What would be an example of one permutation? That would be a permutation in the set on the set 1, 2, 3. What would be a possibility for where we could map 1, 2, and 3 that would give us a function that is onto and 1 to 1?
3, 2, 1.
3, 2, 1. You can map. So you want to map 1 to 3, 2 to itself, and 3 to 1? Okay, that's certainly a permutation. It's 1 to 1. No two elements get mapped to the same thing. And it's onto. Every element in the set from 1 to 3 gets mapped to by something. Come on, Dr. Percival, don't fill them in yourself. That's what you have minions for. What would be another permutation? Actually, you know what? I have a better idea. Take a couple minutes, see if you can find all of the permutations that are going to be in S3. So, I'll give you a hint. There's more than 3 of them, and less than 10 of them. So see if you can find all the different ways that you can map 1, 2, and 3 to the same numbers in a way that is 1 to 1 and onto. Such that nothing gets mapped to more than once, and everything gets mapped to at least once.
Is this group cyclic?
Is this group cyclic? I don't know. Liar. I'll give you a hint. All cyclic groups are abelian. This group is not abelian. Therefore,
It's not.
by the law of modus tollens, as we're going to be talking about in my 105 class tomorrow, it is not cyclic. What? All right, Elaine, let me see your permutations.
Yes, sir.
That one's wrong. If you think you found all of them, see if your neighbor agrees with you, if you feel comfortable talking to them.
Yeah, I thought there was
Elena allowed it and actually looking at you, George, that's going to say this is wrong.
Okay, ready? So,
Yeah.
3, 2, 1.
Yeah, I just got 6.
How many did you get?
1, 3, 2.
But yes,
2,
okay.
2,
I
1.
just thought the noise were on the same page.
I started with these at the top, and then I just rushed it.
I actually did it in a good order. I did it.
And he did.
Yeah, neutral,
Oh, that is chaotic.
This is really chaotic.
I'm miserable. Chaotic
How did
neutral.
you did 3,
I started with the ones
2s,
at
and
the top.
3s.
Sort of like, this was just example.
Well, that's
Then I looked at it as a circle.
As fascinating as this one group's discussion is, let's go back to talking as a whole. So one example that we had was 1 maps to 3, 2 maps to itself, 3 maps to 1. What would be another example? Any groups like to share another example? Thank you.
Just straight across 1 maps to 1, 2 maps to 2, 3 maps to 3.
Ah, the identity function. Yep, you just found the identity element in this group. What would be another example? Mark?
1, 3, 2.
1 maps to itself, 2 and 3 swap. I'm on board with that. Nick, did you have another one?
You could do the same thing, but swap 2 and 1.
Okay, so 3 maps to itself, 1 maps to 2, 2 maps to 1. Okay? So the elements for 1 and 2. All right. What would be, let's give myself a bit more. Another one. 1 maps to 2, 2 maps to 3, 3 maps to 1. So nothing maps to itself. What's that? Calm yourself. What else we got? Right?
3, 1, 2.
1 maps to 3, 2 maps to 1, 3 maps to 2. What else we got? Yes, Elaine?
No more.
No more? You think we found them all? Anybody find any others? Good job. That was it. So it turns out there are 6 elements in this. There's going to be 6 elements in this permutation group, corresponding to the fact that there are 6 permutations of this set. Here's some new notation for you. We can actually denote using a special type of notation called cycle notation, and kind of a clearer and a little bit more of a concise way, what do the individual elements in this group look like. For instance, that is going to be the shorthand way of writing this permutation. And this is going to be called cycle notation. This is a cycle, like a bike, except it looks nothing like a bike. And what this means, when you read this off, I want you to think about the number 1 is going to map to the number 3, the next element that comes after it. The number 3 is going to map to the number 2. And then the 1 at the end of the cycle is going to map back to the first element. So when we write out 1, 3, 2, and using cycle notation like this, we just mean 1 maps to the first thing, maps to the second thing maps to the third thing, etc., etc. Last thing maps back to the first thing. And just writing out 1, 3, 2 like that is kind of a nice, easier, it's a more concise way of saying it's the function that maps 1 to 3, 2 to 1, and 3 to 2. What would the cycle notation look like for this top one here on the left-hand board? The function that maps 1 to 2, 2 to 3, 3 to 1. How could we write that in cycle notation?
Doesn't it map 1 to 2?
It does map 1 to 2. Let's see, well 1 is mapping to 2. 2 is mapping to 3. You want 3 to map back to 1. So that's what you propose that that cycle is? What if I said you're wrong? It's actually 2, 3, 1.
That's the same.
They're actually the same thing. I'm just being mean. Yes, yes, that's absolutely right. In general, there can be more than one way to write your cycles. Just because it doesn't matter which element comes first. It just matters what's kind of the order after the first one. So the function that maps 1 to 2, 2 to 3, 3 back to 1 is going to be the same function as the function that maps 2 to 3, 3 to 1, and 1 back to 2. It's mapping all the same numbers to the same numbers. And if you wanted to, you could also write it as 3, 1, 2. And so the way you write your cycles is not necessarily going to be unique. Sort of like how when we were writing elements in the dihedral group, we could write an element as R, let's say in D3. We could also write it as R to the 4th. And even though they look a little bit different, they're really the same element, because they're going to produce the exact same results if you rotate a triangle once 120 degrees as if you were to rotate it 4 times. Except one leads to a twisted arm. How about this one? Or, no, that's the hard one. Let's do this one. Yes, Elaine?
I was gonna just ask what you do when it maps to itself.
Egad, what do you do when something maps to itself? Oh no. I would do it like this. 1 maps to 2, 2 maps to 1. 3 maps to itself. And it's usually understood that if you have one of these numbers that maps to itself, you just don't include it. So I would say this is going to be the cycle that maps 1 to 2, 2 to 1, and if we don't include the 3, if we don't mention the 3, we just assume that 3 maps to itself. How about this one, where 1 maps to itself, 2 maps to 3, and 3 maps to 2? What could we put in the cycle that would correspond to this element? Okay.
Just be 2, 3.
I disagree. I want it to be 3, 2. But yes, 2, 3 works just as well. I'm sorry, I'm just being cheeky. But I'm also doing it to make a point of that there's not a unique way of typically writing these. I'll do this one for you. This one's going to be 1, 3. And then again, since we're leaving the 2 off here and the 1 off here, we're just assuming that whatever we leave off maps to itself. How about this one? The identity. But how would you write the identity element as a cycle? That look like a cycle?
With parentheses.
Like this?
There we go.
Excuse me, is E an element of the set 1, 2, 3?
Depends on.
Because if you set E equal to 2. So the way we typically, so oftentimes we just denote the identity element. We don't want to just write nothing and say, oh, everything maps to itself, so we don't need to write any cycles. Well, that would just be confusing. So typically we would just write like, just 1 in parentheses. Or yes, Lauren, you could also just write E, and it should be clear, and it'll be clear to people. It's the identity map that maps all the numbers to itself.
If I leave any questions blank on the midterm, will you just assume I'm being math?
Yes, and when I refuse to give you a grade, you can assume that that's also your grade.
Identity. What's the grade in that?
Here, give it E. Actually, fun fact, when I was in grade school, we had this weird grading system. It was EPSIF, so E was the equivalent of an A.
There we go. Bring it back.
These are all, the letters are also to stand for something. Like E was excels, P is progressing, S is satisfactory, I is insatisfactory, F is, you're still a failure. But I'm not going to grade that way, so don't do that. Okay, let's talk briefly about how you would write out the product of 2 elements in here. So here, we're taking 2 different elements in our symmetric group. We're taking the element that permutes 1 to 3, and 3 to 1, and 2 to itself. And we're composing that with the element that maps 1 to 2, 2 to 3, 3 to 1. And I would like to see, how can we simplify this? How can we write this down using a single cycle? Well, this first element is going to map 1 to 3, 3 to 1, and 2 to itself. The second one is going to map 1 up to 2. It's going to map 2 over to 3, and it's going to map 3 back to 1. So if we were to compose these 2 cycles like this, we would get something that maps 1 ultimately to 1. Shoot, I wrote it in the wrong order. I'm sorry, I'm already clubbing this up. We're just, you know what? We'll do this again on Friday. We're about out of time for today. So on Friday, we're going to talk about how to write the products of these things. I did it in a non-standard way, so I flipped it up. And we're going to talk about how you would construct a Cayley table for S3, as well as what happens in S4 that's different than in S3. Because there's something insidious that happens in S4 that does not happen in S3.
I'm guessing
Yep.
yes.
Your guess is what?
My guess is Yes. You're being honest.
Again,
No.
what is different in S4 than S3? Yes is not a correct answer to that question.
But no,